Welcome to qnawire.
Here we have two perpendicular wires which are in the same plane. Let us consider the vertical wire as wire 1 and the wire which is horizontal taken as wire 2. As point P and point Q are at equal distance from wire 1, so we have magnitude of magnetic field at point P and point Q due to wire 1 is equal to mu naught times current through wire 1 divided by 2 pi into distance of point P and point Q from the wire, that is R1. Now we can put different values here. Mu naught is 4 pi times 10 to the power minus 7 Tesla meter per ampere, and current through wire 1 is 12 ampere divided by 2 pi distance of point P and point Q from wire 1 is 15 centimeter, that is 15 times 10 to the power minus 2 meter. This gives us the magnitude of magnetic field at point P and point Q due to wire 1 equal to 1.6 times 10 to the power minus 5 Tesla. Similarly, we can write the magnitude of magnetic field at point P and point Q due to wire 2 as B2 equal to mu naught into I2 divided by 2 pi R2. Again putting the values here, mu naught is 4 pi times 10 to the power minus 7 Tesla meter per ampere into current through second wire is 10 ampere divided by 2 pi into distance of point P and point Q from second wire is 8 centimeter, that is 8 times 10 to the power minus 2 meter. This gives us B2 equal to 2.5 times 10 to the power minus 5 Tesla. In part A of this problem, we are considering the direction of current in wire 2 is from left to right. Now we want to find the net magnetic field at point P and point Q due to these both wires. First, we will take the point P. At point P, we can find the direction of magnetic field produced by wire 1 and wire 2 by using right hand rule. So by right hand, it is clear that the direction of magnetic field at point P due to wire 1, that is B1, is into the page. Also, due to second wire, magnetic field is also into the page. So we will have the net magnetic field at point P equal to B1 plus B2 as B1 is equal to 1.6 times 10 to the power minus 5 Tesla plus B2 is 2.5 times 10 to the power minus 5 Tesla. This gives us net magnetic field at point P equal to 4.1 times 10 to the power minus 5 Tesla, and this is the magnitude of net magnetic field, and here direction of net magnetic field is into the page. Similarly, we can find the magnetic field at point Q. The wire 1 produces magnetic field at point Q, that is out of page. Also, the wire 2 produces magnetic field which is out of page. So we have net magnetic field at point Q, that is also out of the page, which will be equal to B1 plus B2, as we have B1 equal to 1.6 times 10 to the power minus 5 Tesla, and we have B2 equal to 2.5 times 10 to the power minus 5 Tesla. This gives us the net magnetic field at point Q equal to 4.1 times 10 to the power minus 5 Tesla, and here direction of field is out of the page. Now in the second part of this problem, we are considering the direction of current in the second wire from right to left, and we want to again find the net magnetic field at point P and point Q. First we will take point P. At P, the wire 1 will produce a magnetic field that will be into the page, and wire 2 will produce a magnetic field that will be out of the page. Now we can easily see this by using right hand rule. Now we can find the net magnetic field at point P, which will equal to B2 minus B1, as we have B2 equal to 2.5 times 10 to the power minus 5 Tesla minus B1, which is 1.6 times 10 to the power minus 5 Tesla. This gives us the magnetic field at point P equal to 0.9 times 10 to the power minus 5 Tesla, or we can write this as 9 times 10 to the power minus 6 Tesla. Here B2 is greater than B1, therefore the net magnetic field at point P will be in the direction of B2, that is B, that is the magnetic field at point P will be out of the page. Now at point Q, wire 1 will produce magnetic field that is out of the patch at point Q, and wire 2 will produce magnetic field that will be into the patch. Now we can write the magnetic field, that is the net magnetic field at point Q, equal to B2 minus B1. We have B2, which is 2.5 times 10 to the power minus 5 Tesla, minus B1, which is 1.6 times 10 to the power minus 5 Tesla. This gives us the net magnetic field at point Q equal to 9 times 10 to the power minus 6 Tesla. Here B2 is greater than B1, therefore the direction of magnetic field at point Q, that is the direction of net magnetic field at point Q, will be in the direction of B2, that is into the patch.